Cell 1. In this cell, we're delving into the innovative concept of retrieval augmented generation, or RAG, which significantly enhances the capabilities of large language models by incorporating external data sources. This approach is particularly crucial because it allows these models to produce more accurate and factual responses, reducing the chances of misinformation while accessing timely data without the need for constant retraining. At its core, the RAG methodology relies on two powerful types of databases: vector and graph databases. Starting with the vector database, its primary function is to identify and retrieve the most relevant text passages based on semantic similarity. It operates by storing text chunks, embeddings, and relevant metadata, like document identifiers, author details, and timestamps. When a user poses a question, the system transforms that question into a vector and searches for the closest matching text chunks, returning the top results to inform the language model's generation process. Now, let's contrast this with the graph database, which excels in modeling relationships between various entities. Instead of focusing solely on textual similarity, it emphasizes the connections between nodes representing entities like companies, people, or products. When a question is asked, the system identifies relevant entities and navigates their relationships, retrieving supporting facts or document sections that deepen the context provided to the language model. This capability makes graph databases exceptionally useful for complex queries that require multi-hop reasoning. One key takeaway here is understanding how the two databases serve different needs. While the vector database is about finding the closest textual match to a query, the graph database focuses on the intricate web of relationships and how they connect back to the inquiry at hand. As we move forward, the next cell will likely explore practical implementations of RAG, showcasing how these retrieval techniques can be applied in real-world scenarios. Cell 2. In this cell, we're exploring the fundamental differences between two types of databases: vector databases and graph databases, which are essential for understanding how different data storage and retrieval methods can enhance our applications. The emphasis here is on the distinct types of queries these databases can handle, which directly impacts how we retrieve and interpret data. Vector databases excel in processing queries that seek to find text similarity. When you ask, "What text is most similar to this question?" the vector database employs various mechanisms to understand the nuances of language and context, often relying on techniques from machine learning and natural language processing. It transforms text into a numerical form, known as vectors, allowing it to calculate similarities efficiently. This process is crucial for applications like recommendation systems, where understanding user intent and preference can significantly enhance the user experience. On the other hand, graph databases focus on relationships between entities. When posed with a question like, "What facts or entities are connected to this question and how?" a graph database delves into the connections, considering the nodes and edges that define the relationships. This contextual understanding allows for complex queries and insights about interconnected data, making it invaluable in scenarios like social networks or knowledge graphs, where relationships are just as important as individual data points. As we consider these differences, it's important to highlight that each database type has unique strengths and weaknesses, which can significantly influence the design of our data architecture. One limitation to be aware of is that vector databases may struggle with relational queries that a graph database handles seamlessly, while graph databases may not efficiently perform vector-based similarity searches. Looking ahead, the next cell will likely build on this foundational understanding by diving deeper into practical applications of both database types. We will examine how to implement these concepts in real-world scenarios, perhaps exploring specific use cases or algorithms that leverage the strengths of each database type effectively. Cell 3. In this cell, we're diving into the process of extracting and organizing text from PDF documents, which is a critical step for preparing data for tasks like vector search and retrieval. The ability to convert PDFs into a manageable format allows us not only to analyze the content, but also enables machine learning models to interact with this text effectively. Initially, we establish a directory where our PDF files reside, setting the stage for our text extraction. The core function here, extract PDF text, opens each PDF and reads its pages, appending the extracted text along with the corresponding page numbers into a list. This ensures we keep track of where each snippet comes from. Once we have this text, it undergoes a cleaning process. The clean text function is quite crucial here. as it removes superfluous whitespace, making the text more uniform and easier to work with later. After cleaning, we implement a chunking strategy using the chunk text function. This function divides the text into manageable pieces, allowing each chunk to be processed independently. We've specified a chunk size of 800 characters, with a slight overlap of 150 characters between chunks. This overlap is important, as it helps preserve context when analyzing text across chunks. As we iterate through each PDF in the specified directory, we check if the file ends with a PDF extension, and then call our extraction and cleaning functions. For each chunk generated, we compile a comprehensive record that includes the document's name, path, page number, chunk identifier, and the actual text. This structured approach helps us create a well-organized data frame that captures all the necessary details. Finally, we print out some basic information about the resulting data frame, confirming the number of chunks extracted and providing a glimpse at the first few entries. This structured output is vital for the steps that follow, enabling us to efficiently search and retrieve the information we need. Looking ahead, the next cell will likely build on this foundation by focusing on how to implement retrieval mechanisms or possibly integrate this text with algorithms that perform more sophisticated analyses. Cell 4. This cell is focused on leveraging the power of text processing to conduct a search over document chunks using the TF-IDF method, which is essential for understanding relationships between words and phrases in text data. The goal here is to enable efficient retrieval of information based on user queries, helping to uncover relevant content within a larger dataset. To achieve this, we first import necessary libraries, specifically the TF-IDF vectorizer from scikit-learn, for transforming our text data into a format suitable for analysis. We set the vectorizer to filter out common English stopwords, and we include both unigrams and bigrams, allowing us to capture single words and pairs of words to get a more nuanced understanding of the text. After fitting the vectorizer to our document chunks, we create a sparse matrix representation of these chunks, which will be our foundation for similarity computations. Next, we define a function called vector search, which takes a user query and an optional parameter indicating how many results to return. Inside this function, we first transform the query into a TF-IDF representation. The real magic happens next, where we calculate the cosine similarity between the transformed query vector and our matrix of document chunks. This measures how alike each chunk is to the query, producing a range of similarity scores that allow us to rank the chunks. The top results are then extracted and organized into a readable format, including metadata like chunk identifiers and document names, along with their respective similarity scores. This function is versatile, allowing adjustment of the number of results returned, which can be particularly useful depending on the user's needs or the specificity of the query. As we wrap up this operation, it's important to keep in mind that while the TF-IDF method is robust, it may not capture contextual nuances, especially with subtle compound phrases. In the next cell, we'll likely explore how we can further refine our search results or integrate more advanced techniques to enhance relevance and accuracy in our information retrieval process. Cell 5. In this cell, we're focusing on the creation of a directed graph that serves to represent the relationships between various entities, chunks, and documents. This is an essential step in building a framework for graph-based search and retrieval, as it sets the foundation for understanding how different pieces of information are interrelated. The cell begins with the import of the NetworkX library, which is vital for constructing and manipulating complex networks, allowing us to model our relationships effectively. We initialize a directed graph, which means that the connections between our elements will reflect the directionality of the relationships we intend to analyze. The next key part is defining a vocabulary of macroeconomic terms. This set consists of several key phrases and concepts that we anticipate will be prevalent in our data. It's a good idea to expand this vocabulary later as you explore more topics or datasets. There's also a regular expression designed to identify acronyms, which ensures that we don't miss out on important, abbreviated terms that are crucial for extracting insights. The extract entities function is a centerpiece of this cell. It processes a given text by converting it to lowercase, and then checks for the presence of our macro terms and any identified acronyms. It collects these entities, ensuring they are unique, and sorts them for easier analysis. Moving to the main workflow, the code iterates over a data frame containing chunks of text categorized by documents. For each chunk, nodes are added to the graph for both the document and the chunk itself, denoting their types. Edges are created to establish a contains relationship between the document and its chunks, creating a structural mapping of how different elements are related. For each chunk, entities are extracted using our previously defined function. This allows us to connect these entities back to their corresponding chunks, thus establishing relationships that indicate where these entities are mentioned. The final output of the cell provides a summary of how many nodes and edges have been created, offering a glimpse into the graph's complexity. As you consider your next steps, this groundwork will be pivotal for tasks such as querying the graph to retrieve relevant information or performing further analyses to derive insights. The next cell is likely to delve into how we can leverage this constructed graph to enhance our search capabilities, perhaps focusing on specific queries or analytical tasks. Cell 6. In this cell, we're diving into a key process for searching and retrieving relevant information associated with specific entities from our dataset. Understanding how to effectively retrieve evidence chunks can greatly enhance our ability to gather context, especially when analyzing complex topics like economic indicators. The first function, graph evidence for entity, begins by checking if the specified entity exists within our graph structure. If it's not found, the function safely returns an empty list, avoiding unnecessary errors down the line. When the entity is present, it retrieves associated chunks based on a specific relationship type. Here, we're looking for chunks marked as mentioned in. This creates a focused output that gives us the top chunks related to our entity of interest, limited to 5 by default. Next, we see how the getChunkText function works. This function takes individual chunk IDs and looks them up in a data frame to extract relevant information, including the document name, the page number, and the snippet of the text. This is where we start turning raw chunk IDs into meaningful contextual information. After that, there's a process that leverages these functions to get a more granular look at our data. The hybrid retrieve function is where we bring everything together. First, it performs a vector search based on a user-defined query, pulling the top results. It then collects unique chunk IDs from these results and extracts any entities found within the associated text. This is crucial because it allows us to expand our search by linking entities to additional chunks in the graph. The final stage in hybrid retrieve is where we merge everything back into a clean output. By filtering our data frame based on the collected chunk IDs, we create a comprehensive result set that helps answer the original query. Toward the end, we print out the entities that were identified and a sample of the context surrounding those entities, which serves to pique our interest in further exploration. As we move into the next cell, we'll likely build on this foundational retrieval process, perhaps focusing on deeper analyses or visualizations of the extracted relationships. This will provide invaluable insights into how these entities interact within the broader framework of our study. Cell 7. In this cell, we're executing a hybrid retrieval approach that combines vector search and graph exploration to enhance information retrieval, particularly relevant in retrieval augmented generation systems. This method is pivotal, as it allows us to not only find the most relevant chunks of text for a specific query, but also enriches our understanding by uncovering related entities and contextual information. The workflow begins by performing a vector search using the specified query. Here, we limit the search to a defined number of top chunks using the kvec parameter. The results from this vector search are collected into a set, ensuring that we have a unique collection of chunk identifiers. This initial step is crucial, as it lays the groundwork for the type of information we will explore next. Once we have our top chunks, we extract entities from them. This is done by iterating over the text of the identified chunks and using an entity extraction function, which systematically identifies important terms or concepts within the text. These entities provide deeper context and act as essential connective tissue in our subsequent analysis. Now we pivot to leverage the graph structure. For each entity we've identified, we look for additional chunks that are graphically linked to it, expanding our context space. We cap this expansion at a set number, determined by the kexpand per entity parameter, to maintain focus and avoid information overload. The aggregation of these related chunks into our earlier collection further enriches the results. Finally, we filter our original chunk dataset to include only those chunks identified in our enriched collection and format the output to show the relevant identifiers along with the document names, pages, and text snippets. Importantly, this operation highlights both the unique chunks and the entities we found, providing comprehensive insights into the query. Assumptions here are centered around the reliability of the vector search and entity extraction functions, as well as the interconnectedness of the entities in the graph. A common pitfall to watch out for in this process would be the potential for overlapping or redundant information, which could skew our understanding. Looking ahead, the next cell will likely build on this output, perhaps focusing on how to effectively utilize these results for further analysis or response generation, allowing us to draw not just information, but insights from our rich dataset. This creates a pathway toward developing more sophisticated interactions and answering complex queries. Cell 8. In this cell, we're tackling a crucial consideration when working with PDFs, particularly in the context of our analysis. It's essential to understand that not all PDF documents are created equally, and this variability can significantly affect our data extraction process. Specifically, scanned PDFs often pose a challenge, as they can yield a lot of empty text when we try to extract information from them. This issue arises because scanned documents are typically images of text, rather than text files. Therefore, they don't follow the same extraction processes that we can rely on for more straightforward documents, like reports or academic papers. In these latter cases, tools like pypdf generally perform quite well, allowing us to access the content seamlessly. However, when faced with the challenge of a scanned PDF, we can expect to encounter empty or garbled text output, indicating that we will need to employ optical character recognition, or OCR, to convert those images into usable text. This additional step can increase the complexity of our project, as OCR can be time-consuming and may require additional libraries or tools. Thankfully, in the context we've set up for our analysis, we have the advantage of working with PDFs that won't present these hurdles. By recognizing these nuances, we can better anticipate potential setbacks and streamline our workflow. As we move forward, it will be important to keep this knowledge in mind, especially when we delve deeper into extracting and analyzing data from various sources. In the next cell, we'll likely begin applying our extraction techniques, so understanding these limitations will help us prepare for whatever types of documents we encounter. Cell 9. In this cell, we're delineating when to choose a vector database versus a graph database, which is crucial for effectively managing and retrieving information from varied data types. Understanding these differences can guide us in implementing the right database approach that aligns with our specific use case scenarios. Beginning with the vector database, it's most suitable when you're primarily handling unstructured text, like PDFs. This is ideal for situations where your inquiries often involve tasks centered on find and summarize. For instance, when someone asks to summarize a policy or clarify information about a contract, the vector database can quickly process and return meaningful responses. This is particularly pivotal if you are working in an environment where time to delivery is a priority and quick insights are needed. On the other hand, if your needs lean towards multi-hop reasoning, a situation where you might need to make connections through various data points, a graph database is your best bet. This database shines in applications that require auditability and the ability to trace citations. If we consider an example like identifying which policies support a specific decision or uncovering connections among customers linked to suspicious activities, the graph database will provide the capabilities needed to perform these complex queries. As we weigh our options, it's essential to note that using a vector database may lead to limitations in auditability, while a graph database may require more upfront structuring and management of your data. These considerations are important for ensuring that we can maximize the effectiveness of our data retrieval and analysis endeavors. Looking ahead to the next cell, we'll delve deeper into practical implementations of either database type, exploring how to structure data for optimal performance based on the insights we've just discussed. Cell 10. In this cell, we're focusing on identifying the primary risks associated with Apple, particularly emphasizing those connected to the supply chain. This is essential because understanding these risks allows stakeholders to make informed decisions, whether you're an investor, a supply chain manager, or simply someone keen on following industry trends. The cell outlines two distinct approaches for extracting and processing this information: a vector database method and a graph database method. The vector DB method aims to quickly retrieve snippets that mention Apple risk factors supply chain. It offers the advantage of being straightforward and fast. But there's a notable limitation. If a data chunk discusses supply chain risks without explicitly using that terminology, it could get overlooked, leaving gaps in our understanding. Conversely, the GraphDB approach takes a more structured route for analysis. Here, we define key entities: Apple, risk factors, supply chain, and disruptions, and then navigate through relationships among these entities. For instance, we start at Apple, find mentions of risk factors, categorize them, and pinpoint the ones related to the supply chain. This method enhances precision, allowing us not only to filter with great accuracy, but also to trace back to the original sources or citations, which can significantly bolster the credibility of findings. However, this method has its own caveat. It requires a pre-existing graph, meticulously built from previous data extraction, which can be resource-intensive. As we push forward into the next cell, we will likely delve deeper into the findings from our chosen approach, evaluating the identified risks and exploring their potential impact on Apple's operations. This transition will enrich our understanding of how these risks specifically interact with the broader supply chain context. Cell 11. In this cell, we're establishing a connection to the source files we'll be working with, specifically the PDFs stored on Google Drive. This step is crucial because it sets the stage for subsequent analyses, allowing us to extract valuable information from these documents. The process begins by identifying the URL of the Google Drive folder that contains our PDF files. Once we've specified this URL, we can implement code that will facilitate downloading or accessing these files directly within our notebook environment. This action not only saves time, but also ensures our workflow remains efficient as we work through our project. To make this connection, it's important to understand the structure of the Google Drive sharing settings. If the files aren't publicly accessible, or if we don't have the right permissions, we won't be able to proceed further. Therefore, learners should always check the accessibility settings to avoid encountering roadblocks later. As we implement this, we can anticipate that the subsequent cells will build on this framework, focusing on extracting data from these PDFs. The ability to access the files seamlessly will enable us to concentrate on extracting insights, rather than wasting time on navigation issues. Going forward, we'll delve into methods for processing these PDF contents, evaluating the text within them, and pulling out the specific information that will inform our analysis. Having laid the groundwork now ensures a smooth transition into those exciting steps ahead. Cell 12. In this final cell, we're wrapping up the analysis and shining a light on the conclusions we've drawn from our work. It's crucial to take a moment to reflect on what we've accomplished and ensure that we understand the implications moving forward. Throughout the notebook, we've gathered data, performed calculations, and created visualizations that have guided our exploration. By synthesizing everything, we can pinpoint the key takeaways and understand how they fit into the larger picture. This final cell acts as a summary that reinforces our findings and solidifies the knowledge we've built. As we review our results, it's important to think about the assumptions behind our analysis and where potential pitfalls may lie. For example, have we properly accounted for any outliers or considered how our data might vary under different conditions? By critically examining these aspects, we can bolster the robustness of our conclusions. Moreover, thinking about future applications is essential. How can we use what we've learned to inform decisions or further research? There are always new questions to explore, and our analysis serves as a launching pad for those inquiries. Looking ahead, the next steps might involve deeper exploration into the underlying trends we've identified, or even expanding our dataset to see how our findings hold up in different contexts. This process of continual learning and adaptation is what drives us to become better analysts. So, let's be excited about where this journey will take us next.